In this video, we'll move on to section 3.7, which is all about improper integrals, and you'll learn why they're called improper very soon. So let's define. There's three kinds of improper integrals, and basically you have an improper integral if one or more of the bounds is infinite, and that's what we mean by improper, right? Because it's not a defined area from A to B like we're used to seeing. So the first one, you're gonna let f of x be continuous over an interval of the form a to positive infinity. Then when you do the integral of f of x from a to positive infinity, what you're gonna do instead, right, because we don't know how to integrate something and plug infinity in it, right, we're gonna just take away that infinite bound and make it finite, and then we'll just, after we do the integral, we'll then do the limit of that, right? And this all depends on the limit existing, which, remember, just means that the function has to approach the same number from both sides. So let f of x be continuous over an interval of the form negative infinity to b. Then, right, if you want to integrate f of x from negative infinity to b, similarly, right, what we're going to do is get rid of that infinite limit since we don't know how to deal with it, and then we're just going to take the limit of that as it approaches negative infinity. And again, we need the limit to exist. And then lastly, right, this is the case when you have both bounds infinite. So in this case, right, we need f of x to be continuous over the whole real number line. Then the integral from negative infinity to infinity of f of x dx is, right, remember we could split up the interval that we're trying to integrate, right? So we're going to take from negative infinity to 0, so we're splitting it up at 0, and then add on the integral from 0 to positive infinity, right? And we already learned how to do these kinds of integrals, right? We're going to use this for this one here, right? And then we're going to use this for this one here. Okay. Right, and then those limits also have to exist. So we have new vocabulary words which say okay. So in the new vocab words we have, in each of these cases, if the limit exists, then the improper integral is said to converge. And we're going to hear that word a lot in the next chapter that we do on series and sequences. If the limit does not exist, then the improper integral is said to diverge. Okay, so when we get convergence, we get an actual value for the integral. If we have divergence, then we don't. Right, so in this last case, if either one of these integrals diverge, then the whole thing diverges. Okay, so let's do a couple examples. So the first example that we're gonna do says to determine whether the area between the graph of f of x equaling 1 over x and the x-axis over, right, so that's the definite integral, remember, between the curve and the x-axis, that's just the definite integral, so don't let that trip you up, over the interval 1 to infinity is finite or infinite. So what we're trying to find is the area from 1 to infinity, and our function is 1 over x. Right, so what we learned is that we want to get rid of that infinite bound and change it to t, and then we'll just take the limit as t approaches infinity. Right, so then we do the integral first, and we know that this integral is the integral of ln of the absolute value of x at 1 and at t. Right, so this is the limit as t approaches infinity, and then I have ln of the absolute value of t minus ln of the absolute value of 1. And remember that ln of 1 is 0 because e to the 0 is 1, right? And ln is, what do we raise e to? And then we do the limit as t approaches infinity of ln of t, right? And when you're doing limits, right, remember you could plug in a bunch of values, right? Or you could think of the graph. So how I always like to do this, first I remember that e to the x and ln of x are inverses, and inverse functions, their graph reflect across the diagonal. So it always helps me, like sometimes I forget what ln of x looks like if I'm being honest, but I can always graph e to the x pretty easily because I know if I plug in 0 into e, that's going to give me 1. And then I know if I plug in positive numbers in there, then this is going to get bigger. And then if I plug in negative numbers, right, that's going to send it to the denominator because it's negative number exponent. So it's going to make it smaller. But it's never going to be negative, right, because the base e is positive. So then I know my ln function looks like this. Right, so then when I'm thinking about this limit, as ln goes further and further along towards infinity, it's increasing. So that's going to go off to infinity. So this is actually infinite. So that tells us that the area is infinite, right? And we can see that from the graph as well, because the area that we're considering is this area under here. But that area, right, since ln is going to keep on growing and growing, that area also is going to keep on growing. So that area is infinite. Okay, let's do one more example. So in this example, we're evaluating the integral of x times e to the x from negative infinity to infinity. And we're trying to determine whether it converges or diverges. Right, so remember, when both of the bounds are infinite, what we said we have to do is split this up into two separate integrals. The first one going from negative infinity to 0, and then the second one going from 0 to infinity. We're going to have to solve these separately. So in red, I'm going to focus on this very first one. So first, do the integral from negative infinity to 0 of x e to the x dx. Right, so then remember, we have to address this and take away that infinity, right, and turn it into some finite variable. So I was using t, I'm using b now, it doesn't matter, it means the same thing. So you can use any letter you feel, whatever floats your boat. And then this is the integral we need to do. So what technique can we do, right? This is not just a regular function, right? If this x was in here, then it would be just e to the x, and we could use the antiderivative of e to the x. We know it's e to the x. This is a product of two functions, so that raises our integration by parts flag. So we have to choose a u, which remember we use Liate, so x a algebraic comes before e, which is exponential, so we're gonna make u be x, and then dv is just e to the x, and so then v is just, right, the integral of e to the x dx, which is also just e to the x. And then the derivative of u, right, of 1 is just 1 dx, or simply dx. And then we know the formula, right, is the integral of u dv is uv minus the integral of v du. So I'm going to plug all my stuff in. My u was x, my v was e to the x, minus the integral, v is e to the x, and du is just dx. Right, and that's an integral we can do. We have an antiderivative formula which tells us the antiderivative of e to the x is e to the x. Okay, so now we can plug that in here. So we have a limit as b approaches negative infinity, and then we have x e to the x minus e to the x, but we have to evaluate that at b and at 0. Right, so then let's plug in our bounds. Make sure you don't drop your limit. Right, so first we plug in 0. So it's going to be 0 e to the 0 minus e to the 0 minus. And then we plug in b. Right, so we get b e to the b minus e to the b. Right, and then we know that this is just 0 and this is just 1. So this becomes the limit as b approaches negative infinity of 1 minus b e to the b plus e to the b. Right, remember you have to distribute this negative sign. And then, right, if you notice, right, if we make b go to negative infinity, then e to the b, when b is negative, right, this is going to go to 0, right? Because if we have e to the negative infinity, right, that's 1 over e to the infinity. So that's 1 over a big number, which is going to 0, right? So this is as b goes to negative infinity. So then this is equals, I almost dropped this negative sign here. Negative 1 minus 0 plus 0. So this is 1 is just equal to negative 1. So this first integral converged, right? This one's now equal to 0. And now let's do this one here in purple. So from 0 to infinity of x e to the x dx. Right, so we already solved, right, we're going to change this into the limit. I guess I'll stay consistent with the b goes to infinity of 0 to b x e to the x dx. So the only thing that changed between this integral and this first integral is the bounds, right? So we can actually use this, right? This is the same, x e to the x is the same integral we're finding, so we're still going to get this answer here, right? So this is equal to the limit as b approaches infinity of x e to the x minus e to the x, and then we have to plug in 0 and b. Right, so then we do the limit as b approaches infinity, and we plug in b, and then we plug in 0. Right, so then this simplifies a little bit. So we have b e to the b minus e to the b, and then this is just 0, and then this is 1, right? But when we distribute this negative sign, that's going to become positive 1. And then when we do it as it goes to infinity, right, now this is going to get huge, this is going to get huge, this whole thing is going to get huge, this whole thing's going to get huge, and this thing is even bigger than this thing. So this whole thing is going off to infinity. So that one diverges. Right, so to conclude, since this second integral from 0 to infinity of x e to the x dx equals infinity, that means that the integral from negative infinity to infinity of x e to the x dx also diverges. Thank you.